Right, folks, we're going to talk about constraint optimization. And since Rome wasn't built in a day, let's talk about unconstrained optimization first real quick, even though everyone knows how that works. So the general problem with optimization is that you have a function f which you want to minimize. You might want to maximize it, but then you just put a negative sign and say I want to minimize the negative of that. So this is general enough. The easiest function to minimize is the parabola. I'm sure everyone agrees. Let's make a parabola like this. This is x and this is f of x over here, the guy we want to minimize, and let's call this fx equals x square. And it's easy to see here that at the origin x equal to 0, f is 0, and it is at this point that f is minimized. Now what is special about this point? Well, the tangent at this point to this curve is parallel to the x-axis, and another way of saying that is del f by del x equals 0. Now let's make things a little more interesting. Let's add a y-axis as well. We are not happy with just one dimension, we want two. And now what is f? Well, let's call f x square plus y square. And so instead of a parabola, f is now a paraboloid. Alright, and now what this curve will look like is, it will look the same when y is 0. When y is 0, it will look the same. And when x is 0, it will also look the same, but it will be rotated. So it will then be in the yz plane, and I'm using z to be the same as fx. So z is fx. So in the yz plane, you'll again have a parabola when x is 0, and in this way you'll have this paraboloidal structure. And now if you want to minimize this guy, again what we require, we can see that it's again the origin x0 y0, and here at the origin again we have del f by del x equal to 0 and del f by del y equal to 0. You don't believe me? Alright, so let's work it out. Del f by del x is del by del x of x square plus y square, which is equal to 2x, and del by del y of x square plus y square equals 2y, and at the origin x and y are both 0, which implies del f by del x equal to 0 and del f by del y equal to 0. Now an interesting concept is that of gradients, where you can succinctly state this as del dot f equals 0, and what that means is, what this operator means is del by del x along the x direction and del by del y along the y direction, and when you apply this to f, you get del f by del x along the x direction and del f by del y along the y direction. And as we showed above, this is just 2x and 2y, and at the origin this is the 0 vector. So in order to minimize a function or optimize a function, we need the gradient vector to be 0. Now while we are studying this function, let's look at this some interesting properties of the gradient vector. We see that at any point x comma y, the gradient vector del f is 2 times the vector x comma y, x along the x direction, y along the y direction. So let's go back to the paraboloid up here. So if you have this plane and this is the value of z, let's say, if you go to any point x comma y, so let's say over here, we have x comma y. All you need to do is extend this vector, right, equal to, and like scale it by 2, and that will be 2 times x comma y, and which happens to be your gradient del f. So remember that. Now we've mastered unconstrained optimization. Let's move on to constrained optimization. Let's introduce a really simple constraint C, x comma y, and define it as x minus 5, and let's say we require that x minus 5 equal to 0, which is basically the x equal to 5 plane, a plane that is perpendicular to the x-axis and intersects it at x equal to 5. So if you have your x-axis, y-axis, the plane looks like this, intersecting at x equal to 5, and you have your plane here. Now how does this constraint affect our optimization problem? Well, now you can frame your optimization problem as minimize f equal to x square plus y square, subject to c equal to x minus 5 equal to 0. And this is where we use a concept called LagrangeMultipliers, which basically state that in order to solve this constraint optimization problem, and we are only taking equality constraints for now, you can generalize it to inequality constraints too. Instead of just saying del f equal to 0, which we do for unconstrained optimization, for constraint optimization we define the Lagrangian, which is f plus lambda times c, and we say that in order to solve the constraint optimization problem, we need del L by del x equals to 0 and del L by del C equals to 0. And in general, we'll obviously have not just x but x, y, and a bunch of other stuff. So let's succinctly state that as del dot L equals 0. And del is in this case with respect to x comma y. Right. So what's the intuition behind this, right? So let's go back to the drawing board. You have your x-axis here, y-axis here, and you have your function f here, which we are calling z equal to f. And what does del dot L equal to 0 mean? It means that del by del x and del by del y of L, which is f plus lambda c equals to 0, implies del dot f plus lambda times del c equals to 0, which means del f equal to minus lambda times del c, and this means that del f and del c should be parallel. What's the intuition behind that? Now we know we have our nice little paraboloid here, and we also have our constraint, which is the plane perpendicular to the x-axis, and this is the plane of the constraint which I've drawn here. Now what is the gradient of the constraint? Since you're dealing with del f and del c, let's see what del c is. I've already told you up here how to find del f. Now del c is basically what? So what is c? C is equal to x minus 5. So del c equal to del by del x of x minus 5 and del by del y of x minus 5. This is the vector del c, which is equal to 1 and 0. So it is always pointing along the x-axis, right? And another neat thing about the gradient of a function is that if you are along the gradient, you are increasing the function. If you are against the gradient, you are decreasing the function. But if you are perpendicular to the gradient at a given point, you are not changing the function at all. So if you move perpendicular to del f, you don't change del f, you don't change f. If you move perpendicular to del c at a given point, you don't change c, at least locally. So now let's look at what the Lagrangian condition tells us. It tells us that del f plus lambda times del c equals 0. I got that from here, and this implies del f was 2x and 2y, 2x times 2y, 2x and 2y plus lambda times 1 comma 0 equal to 0. So along the x direction, it says that 2x plus lambda equals 0. Along the y direction, it says that 2y plus lambda times 0 equals 0, which implies 2y equals 0, which implies y equals 0. So we require at the optimum point that y be 0, and we already know that x should be 5 over there, because the constraint, that's what the constraint is, and hence the optimal point is x equal to 5, y equal to 0, and z equal to 5 square plus 0 square equals 25. Now let's look at the intuition behind this. So going to the drawing board yet again, we have xy and our little paraboloid. Now the only thing we ever wanted was to decrease this objective function f as much as we could, but then this constraint came in the way, x equal to 5, and it prevented us from realizing our dream. But far from getting discouraged, we want to minimize f as much as the constraint will allow us to. So how will this constraint interact with this function f? It will be an intersection of this paraboloid with the plane x equal to 5. And if you intersect a paraboloid with the plane, you end up getting a parabola, just another parabola. So now let's look at this parabola in more detail. I'll draw it in a different color. So let's look at this plane x equals 5, and let's draw the the z-axis somewhere behind it, maybe here, and we know that let's draw this point first, the origin x0, y0, z0, and this is where the unconstrained problem is optimized. And let's take the point we already know that the constraint problem is optimized at, which is x5, y0, z25. And now let's take a special point on the z-axis, which is x0, y0, z25. And if we draw a plane from this point perpendicular to the z-axis or parallel to the xy plane, it will end up intersecting this parabola. It will end up being tangential to the parabola at this point. Now let's go further up the z-axis at a point higher than z equal to 25, and x and y are still 0 because it's the z-axis. And let's draw another plane parallel to the xy plane, which is going to intersect the parabola at these 2 points. Excuse me. And we're back. Let's see. Yeah, so as I was saying, we're going along the z-axis, and first we took this point 0, 0, 25, and 25 happens to be the optimum value of the constraint optimization problem. We draw a plane parallel to the xy plane or perpendicular to the z axis, and this plane over here happens to intersect the parabola tangentially at this point here, x5, y0, z25. And then we take a point that's a little above 25, there is 25, so x0, y0, z50 for example, and we again draw a plane perpendicular to the z-axis and it intersects the parabola at point 1 and point 2. Now, as I explained before, if we want to find del f at point 1 or point 2, all we need to do is go along this direction, and this is our del f. Similarly, we'll call this point 3, the one below, which is happens to also be the optimal point, x5, y0, z25, and del f at point 3 is simply an extension of the perpendicular line from the z-axis to this plane. So this is del f3. Del f1 was at point 1 and del f2 is at point 2. And now what about del c? As I mentioned before, del c is always parallel to the x-axis. So it will always be pointing outward and parallel to the x-axis. So at point 1, del c1 will be like this. At point 2, del c1 will also be parallel to the x-axis, and at point 3, del c1 will actually be, del c3 will be parallel to del f3. Now, what does that mean? So if you look at points 1 and 2, what we see is that moving along anywhere along this plane means we are moving perpendicular to del c, because this whole plane is perpendicular to del c, the x equal to 5 plane. So if we move from point 1 along the parabola, so let's do that here, from point 1 downwards along the parabola, we are moving perpendicular to del c1 but not perpendicular to del f1, because del f1 is not perpendicular to this plane. And in general, if we move in a general direction along this plane, we are not necessarily perpendicular to del f1. In fact, what happens at point 1 is that del f1 dot, if we call this direction d, which is, let's say, along the tangent to the parabola, let's call it d1, then del f1 dot d1 happens to be less than 0. Similarly, at point 2, let's call the direction along the parabola d2. We again see that del f2 dot d2 is less than 0, while at the same time del c1 dot d1 is equal to 0, because del c1 is perpendicular to the entire plane, and del c2 dot d2 is also equal to 0. So at points 1 and 2, if you move along d1 and d2, which are directions along the parabola, the blue parabola, you end up decreasing f, because the dot product with del f is less than 0, while at the same time not changing c at all, because the dot product with the gradient of c at both these points for both these directions d1 and d2 is equal to 0. So you are able to decrease f without violating your constraint, which is awesome, because that's what we ever wanted to do, remember? Decrease f as far as we can while being constrained by this c function. So we can keep doing that until we get to this point 3. And at point 3, something special happens. Now del f and del c align. And what that means is that in order to decrease del f further, I mean, it's technically possible to decrease it further. It's f is 25 here, but at the origin here, all the way down there, it's actually 0. So it's possible to go from this point where it's 25 to the origin where it's 0, hence decreasing it further. But if you go towards the origin, you are no longer perpendicular to del c. And in fact, the dot product with del c is less than 0. So if we call this direction that's going from this point 3 towards the origin d3, then d3 dot del c3 is actually less than 0 and not equal to 0. So you end up violating the constraint. And that's the reason that 0.3 is as low as we can make f. You can't make it any lower than 25. If you want to make it any lower, you're moving in a direction that is not perpendicular to del c, and hence you're violating the constraint. So that's the intuition for why Lagrange multipliers work and why we want del f to be a linear scale of del c. We want these two vectors to be parallel. Thanks for watching.